We're going to be relaxing in the living room today because I just don't have the bandwidth for anything else. So if y'all want to look at yourselves, say, ta-da, here we are, ready? Yay! Say hello to, Delia and Sky and Eleanor and whoever isn't here today. Hello. Okay, so let me flip this to my screen so we can, where's the thing? Come on. There we go. All right. Excellent. Okay, so we're going to do our lesson today in PowerPoint because I just threw this together. So we're hoping this is going to work. All right. Very good. Did y'all have an okay weekend? Everybody?
I had a great.
You had a great, well, you were on vacation somewhere, right?
I went to Charlotte North for the NASCAR race.
Oh,
Like,
wow.
up and down. Like, it was awesome.
Is that the first time you've been to a NASCAR race?
Counting all like the lower series races.
Yeah.
But like the big time races.
That's excellent.
Awesome.
All right. If you want, I'll talk to you about it after class. Figure out what's up with it.
I did watch.
You got to answer all the questions.
I did answer all the questions.
They can have. See, look where I marked.
I'm looking where you marked. Every single time you marked, I wrote an answer.
I know, but we'll talk about it. So when you guys are doing your labs and stuff, be sure you answer all the questions and be sure you give very thorough answers, right? We want nice, thorough answers to questions. We don't want, like, look at number 3. Like, sometimes people will do that. They think a similar answer was what they had put for the one above, so they'll say, well, look at that one, I already answered it. But the point is to really think about, usually the question is phrased slightly differently, so there's usually some additional information you can give, or maybe a different angle you can give on that data. All right, so we're gonna go ahead and do lesson 8. Now, my plan of all plans is that next week, when you arrive here, I'm gonna give you your next 9 weeks worth of lessons to put in your binder. I have through lesson 14 done, so I have to do 15, 16, and 17 because lesson 18 is kind of just like a party day, right? Like we're watching a movie and we're having like our little Christmas party. No, we're watching, it's called October Sky. Have you ever seen it? It's a movie about some boys who build rockets because they're inspired by the U.S. space system when it was brand new, like all the NASA stuff and Wernher von Braun and all that. It's really cool. So it's our last class before Christmas. So it's the 17th, I think.
We drink hot cocoa.
Sure. Well, everybody will bring food and we'll chill and we'll watch. It's a good movie. It's a fun movie. All right. So let's go ahead and do this one. So we're getting into Newton's laws. Does anybody think they're going to go to the fair this weekend? Anybody planning on going? Don't know?
I have a big thing at my church.
Oh, do you?
I can't.
Okay.
My
Okay.
mom
Well,
was using me to get in the fair for free.
I am using you to get in the fair for free, but it's all good. So.
I chose not to go. So you saw it.
Oh, well, does anybody else's mother make them do things they don't want to do?
Yeah.
Oh my gosh, look, it's a thing.
Yeah, they don't use their children to get into the place that they want to have fun.
Would your mother use you to get into a place she wanted to get? Okay.
She gives me food. I don't complain.
There you go. I love it.
Sky.
All right, so is that Sky?
I don't like food.
Hello, she's made it.
I
Let me get your papers to you. Oh, there they go.
It's like I say, I'll give you one. I don't like
Have. Here you go, Sky.
I'll give you something.
All right. So, all right, go ahead and get your notes open. Everybody have your notes open. And we're gonna fill in our blanks as we go, and hopefully this will work because I threw this together in about 7 minutes this morning. So this is your notes, but I moved them into a different program. So we're talking about force, mass, and acceleration. And we're talking about which law? Newton's second law, right? Okay. So what was Newton's first law? Do we remember? Yes. Yes. Unless acted upon by an outside unbalanced force. Excellent. You guys got it. All right. So it's object at rest, and object in motion.
I have a question.
Yes, sir.
It said it will remain at rest or remain in motion unless it is hit or stopped by something that is an unbalanced force.
Yes.
Right?
Yes.
But even if it is what if it's a balanced force? It could stop the object, right? Which means it would stop it so it wouldn't remain in motion.
Yeah, it's more the idea of the outside force, but that makes it unbalanced because it. Do you know? See what I mean? No.
Like they're both coming at
Right.
the same amount of
Yes.
newtons.
Mhm.
But one of them is like, and
Yeah.
when they collide, this object over here and over here
Right.
remain in motion.
But that's the outside.
That's not an unbalanced force.
Right. I may have voiced it wrong, but it's the outside force that we're concerned with, or something that knocks it off its course or that starts it moving, right? Okay. So it says we are going to be learning more about Sir Isaac Newton. So it would be helpful to have some more background information on him and how did he come up with his ideas. Newton built on the discoveries of the great scientists before him. So he wasn't coming up with this stuff out of thin air, right? Like he was working with what other people had come up with. He studied Aristotle.
They stole it?
No, he didn't steal it. He built upon it. There's a difference. So it's when you take a theory that's already there and you keep building.
He gave credit to the people
Yeah.
he was building upon.
Yes, he did.
And adding his ideas.
Like he never claimed that he came up with it all. So he studied Aristotle, who had incorrectly proposed that force is required to keep an object moving at a constant speed. Now, why might Aristotle have thought that? Why would Aristotle maybe think, we're talking way, way back, ancient Greece, why might he think you need a force to keep an object moving?
Because he thinks he's distorted.
Yeah. What about the process of an object moving? Like, what's your experience? What keeps a car moving?
And
Yeah, okay, so that's a force, all right. And then if you kicked a ball along a perfectly level surface, is it going to roll forever?
no.
No. What'll happen eventually?
It will stop.
Okay, but why did it stop, Drew?
Off that surface.
No. Why would it stop? Pressure from the air is pushing down on whatever surface is, and what's occurring between the ball and the surface? Friction. Okay, so looking at so looking at this, Aristotle incorrectly proposed that a force is required to keep an object moving at a constant speed. He wasn't taking friction into account. Probably had never considered it, or maybe it just wasn't on his radar at the time. So if you didn't have friction was not an issue, then something would just keep rolling, right? But he's got friction, so from his experience and his observation, you have to keep pushing something to keep it moving, right? All right, and then he also studied Galileo Galilei, who concluded, yes, that objects not subjected to friction, so here now Galileo is acknowledging friction, objects not subjected to friction or another force will continue to move indefinitely. Okay, this is kind of like last week's lab when we talked about Galileo's principle, or he talked about, or Galileo's hypothesis, right? It was that stuff in free fall, an object in free fall will continue to accelerate as long as it's not, in contact with friction, which we really can't observe that unless we create a vacuum and do the activity in a vacuum. Yeah, space is, yeah, but it's lower. It's much lower because the gravity is lower, so the effects of it are lower. But yes, there's friction in space.
Well, what if you were in like what if you were billions upon billions upon billions of, wait, so a light year is a distance, not a time.
Yes, it's a distance.
Yeah, millions and millions and billions, trillions of light years away from everything else.
Yeah.
Space, nothing else.
Yeah.
And just pretend like there were no planets, no nothing.
Okay.
There's no gravity, right?
There's less gravity. Well, all right. There's no planets anywhere.
No planets.
So you have a total and complete vacuum, basically.
Just complete space.
Then there wouldn't be gravity because it's the gravity that's the planets that are creating the gravity's pulling all the things together. Well, that's kind of like, there may be gravity, but we would have no way of knowing it. That's like saying, if a tree falls in a forest and there's no one there, does it make a sound? Because yes, it does, but there wouldn't be any way for us to see it, right? Because you need at least two objects to see the interactions of gravity. But Drew, if you think about like comets, for example, that move through space, they're burning because they're moving through the air, right? That's friction. Just like when the space shuttle used to re-enter our atmosphere, it would burn, or the space capsule would do the same thing. The bottom of it, there'd be fire from all the friction. So let's see. Through his work, Newton was able to define mass and force. Yay, we have definitions now. And he introduced his laws of motion and published his results in the Philosophiae Naturalis Principia Mathematica, which is Latin for mathematical principles of natural philosophy. right, so, oops, all right, here we go. This is always in the way, and there's like, there it is. So our first dude here, this is our man Aristotle. So do y'all see when he was born? 384 BCE. So we're talking 384 before year zero. So that's a long time ago. And where was he? Oh yes, science has always existed. And so where was he educated? Do you see where he was educated? Plato's Academy in Lyceum. So Plato is a very famous philosopher, a Greek philosopher. And he was one of those thinkers who just like thought for a living, basically. He just thought all day, but he thought some really deep things. So, yeah. So where was Aristotle from? What country are we talking about here? Yeah, go ahead. Greece. Yep. Okay. So he's from Greece, and he was born in Greece and he died in Greece. So Aristotle is one of the most famous Greek scientists. He did a little philosophy himself. So then we move on to the next guy. Now look at this. Here's Galileo. Oh wait, Aristotle here's an Aristotle quote. We are what we repeatedly do. Excellence then is not an act, but a habit. I like that. That's a philosophical thought right there, right? So excellence is not an act, but a habit. We should all internalize that one. That's a good one, all right? So now look at Galileo. Okay, here's Galileo. He said, all truths are easy to understand once they are discovered. The point is to discover them. So here you got Galileo, and look when he was born, 1564. So that is 1564. Okay, Alexa, what's 1,564 plus 384?
This might answer your question. 1,564 plus 308 is 1,872.
Well, she said 308, but you get the point. Almost 1,900 years. They're about 1,900 years apart. So the next big think about things moving, the next scientist that made any sort of impact about things moving was nearly 2,000 years later. That's a long time. That's a long time for people to just be like in the mindset of Aristotle and starting to think differently before we get to Galileo. So here we have Galileo, and where was he from? He wasn't Greek. What was he? Yep.
Italian.
He was Italian. Yep. All right. And you can visit him if you go to the Basilica di Santa Croce in Florence. And he is buried, he is very much dead there. But that is where his tomb is, along with Michelangelo, Machiavelli, and Rossini. Yeah. Do they have his middle finger? Oh, that's cool. That's very cool. That's weird, yeah.
You have any other finger except that one finger.
Yeah. There is
They just put it down twice.
we don't have it very much here in the US, but especially in Europe and then in other places that are even older than that, where the societies are more established and older, you've got relics, and typically they're from religious figures like saints, but sometimes they're just from important people like this. So Galileo actually had issues with the church. And there's a really good book that my husband read that I mean to read called Galileo's Daughter. His daughter was a nun, a Catholic nun. And he had issues with the Catholic Church because he was talking about what kind of a solar system. Do you remember?
Was he the guy who's burnt alive?
No, I don't think he was. Was he? I'll have to look that up. I don't believe so. I don't believe he was. There may have been a threat.
That was a saint.
It was you're thinking of a saint. I was trying to figure out what you were thinking of. No, but he did have issues with the church, and a lot of people like to make it worse than it was. But the church then came back later and acknowledged he was right. So what were you going to say?
Not just one of his songs.
All of his daughters were nuns? Yeah, the one that the book is about is a nun. How do you know so much about Galileo? Did you visit Florence? Or?
I did a science class.
Oh, you did? On Galileo? That's excellent. Do you know how he died? I was going to look that up.
He had his last years on house arrest.
Oh, under house. Yeah. I thought he was under house arrest. Yep. But yeah, so they came back years later and they were like, yeah, sorry, we weren't so nice to him. He's totally right. Right. But at first it was just crazy because especially in Italy, near the Vatican and the seat of the Catholic Church, which was the church of all churches at the time, right? And still is pretty darn big church. They had influence over, everything, policy. Do you need help with that, Trav? And they basically,
Here, Trav, let me.
there you go, guys. So they basically disagreed with him and said that it was heretical, right? Like that what he was saying was not cool, did not follow their rules. So the last dude here we have is Newton. And so we have a Greek guy, an Italian guy, and Newton was what?
Was Charles Newton, was he also being shamed for?
Not so much. No, it's American. What was he? Yeah, he was British. Yeah, Jackson Scott. He was British. Okay. So Newton was born in 1643. So not that much longer after Galileo. If you look, Galileo died, and just less than a year, 4 days shy of a year later, Newton was born, right? So Newton said, what we know is a drop, what we don't know is an ocean. And I think that's probably true of a lot of things. So he was at Cambridge and Trinity College and King's School, which are all still there. These are all still universities that are functioning years and years later.
Funny, all these old people that are like old scientists and really famous people, they always are poets.
Poets? Oh, you mean they speak beautifully? It's because everybody used to talk like that before people started texting and abbreviating everything. Yeah. So yes, pip pip.
Then New York came along, like, get out of the way.
He's interred at Westminster Abbey in London. There you go. And along with him at Westminster Abbey, you'll find Queen Elizabeth I, Charles Darwin, Charles Dickens, Michael Faraday, who's also somebody we will study this year, Stephen Hawking. You guys probably know he was a contemporary. He died just recently. I think he's the most recently interred person there, but I could be wrong. And Shakespeare. So he's in very good company.
Shakespeare was a scientist?
No, just people buried at Westminster.
Oh, okay.
Yeah. So now here we go into the actual notes here. So according to Newton's something law, an object at rest remains at rest, an object in motion, constant velocity will continue moving at a constant velocity unless it's acted upon by an unbalanced force. So Jackson, which one was that? Which law? That's the first law. Okay, there we go. So, okay, well, we'll talk, you and I'll chat about it. We'll discuss it. So sometimes Newton's first law is called the law of inertia. Inertia is the tendency of an object to resist change in its motion. So blank, in other words, means that an object in motion tends to stay in motion, and an object at rest tends to stay at rest. What word do you guys have there? What do you have? Inertia. Okay, there you go. So you see this dude on the motorcycle, and he's like barreling along there with this seriously,
When I lose this Fortnite face.
Yeah, he's yeah, and then he hits the wall, and over he goes.
His street
You like him? He's cool, right? Yeah.
We don't see what the object comes at rest because
I like how he's pointing at the wall as he goes over, like, whoa, where'd that come from? Like he didn't see it.
He's in the same pose as he was when he was driving the motorcycle.
Yeah, he is.
we won't see
His legs are straight in all cases.
we won't see when the object comes to rest because that
Yeah, that may not be so good looking when he comes to rest. So this is kind of, so Drew, we're going to kind of use this whole process, this whole theory here today for our lab. So our lab today is we're going to create these little rolling cars with an egg in it, and your team is going to try to restrain the egg so it doesn't do like this dude does. Now this is why we have seatbelts in cars, right? And now we have airbags because if you think about it, if you have to stop really hard in your car, even though your airbag may not come out, where does your body go in the seatbelt? Like what happens to your body? Yeah, you go forward, and then once you stop, where do you go? Back. So there's your so there's your equal and opposite, right? Forward and back. So that forward motion is your inertia, like you're moving. It can sometimes if it stops hard enough. You stop a car hard enough, it can upend, right? But usually the brakes don't lock hard enough. Now they don't lock anymore at all. New brakes don't lock at all. Anti-lock brakes. Not that thing out there. It's a totally different story. Yeah, but you know how anti-lock brakes work? So they squeeze and let go really fast so that you don't ever just clench the brake pad and stop the tire. Like in an old car like mine out here, when you hit the brake pad clenches down, right, and it stops the wheel from turning Entirely.
Race cars.
Yeah.
And stuff.
It's like on your bike. When you stop, you hit your brakes really hard. Same thing happens in that car. Well, the thing is, you can swerve, you can spin around. It depends on like which brakes lock, you know. So it's a very different process.
I'm
Mhm.
surprised the guy's talking about when he was gone.
Man, gotta put that in, don't bite it off. So Newton's second law states that the what? What do you got? The net force on an object, if it will go, okay, is equal to the product of its what and its what, Trav?
Acceleration in its mass.
Yes, perfect. All right. Do you remember what I said net meant? Does anybody remember? Remember?
Like if you add two things
Mhm. Yep.
subtract. It's
Either way. Yep.
Like a
It's like
network.
the answer.
Yeah, it's usually subtracting. Yeah, it's usually the difference. That's what we're talking about. And it's how much is left after you take everything away, right? All right, excellent. Very good. So we have force equals mass times acceleration. Now, you guys are going to want to start memorizing these little formulas about force and force equals mass times acceleration. And we're going to have a couple of them this year that you're going to want to memorize. So if there's something that helps you do that, like if it's a flashcard or writing it down on your bedroom wall so you see it or whatever, or dry erase marker on your window in your mirror in your bathroom, so every time you go in it's there, whatever works, because you're going to see them a lot. All right, so the unit used for acceleration is what? It's the meter per second squared. Yep. And remember, that's because it's per second, right? Do you know what the next one is, Jack? The unit for mass is? Kilograms, right? Okay. So the unit for force is the Newton. How do we abbreviate Newton? An N. Is it a lowercase n or a capital N? It's a capital N. Yep. Very good. All right. And you will find that there are going to be certain things in science where a lowercase letter and a capital letter are abbreviations for two entirely different things. So.
Yeah, I noticed that when I was doing my math,
Mhm.
and it was D and then D-A.
Oh.
It was DESA.
DESA and DECA.
And I didn't know that, so I wrote every single answer wrong.
Yep, you did. But you'll find, like, for example, density and distance, those are going to be different. All right, so 1 Newton is equal to the amount of force that causes a blank mass to accelerate at blank. Yes, Trav? Yep, a kilogram mass to accelerate what? Anybody know? You got it, Jackson. 1 meter per second. Excellent. So you take a 1 kilogram mass and you make it move at 1 meter per second. So you make it cover a meter in 1 second, and you have a Newton. I can even get like a kilogram mass upstairs and a meter stick, and we go, whoop, a Newton. I mean, that's basically what a Newton is. So acceleration is determined by the following equation, and that is force divided by mass. Dude, no, I don't know who you are. I have no idea. All right, so here we go with this one. Increasing the force or blank, the mass increases acceleration. It's decreasing. It's a specific kind of change. So if you increase the force or decrease the mass, you can increase the acceleration. So here's your box. See the girl with the box? If she moves the box, she's accelerating it, right? But if she takes the same amount of force, like in the second picture, and she accelerates 2 boxes, they're only going to go half as far with the same amount of force, right? If you think about it like a tank of gas. If you got a tank of gas and you can go 100 miles, if you only have a half a tank of gas, you can only go 50 miles, right? Same kind of thing. So the next one is the same thing here. It's the increasing the mass or decreasing the force can decrease the acceleration. So if she has 3 boxes, she can only get 1/3 as much acceleration. All right, does everybody have all of that?
I have a question.
Yes.
Why is he so weak?
I don't know. Maybe there's cinder blocks in those boxes. There you go. She's not getting enough exercise.
She's also.
Hold on, I'm not double side.
Yeah, she's wearing a skirt, and yeah, I don't. When I move boxes, I typically don't go around in a skirt. But you know, maybe it's just me. I don't know. All right, so these, you got it, Lily? Write those 2, decreasing, and then we'll look at these questions, and we're gonna share our answers real quick. All right, so what is Newton's first law in your own words? Somebody tell me. Drew, what do you want to say? Newton's first law in your own words.
Objects that is in the motion, but
Yeah.
it's like an object that is moving will continuously move unless something else, it doesn't really matter what, stops it from moving by either hitting it or just staying still and having
Stops it
someone else
or
hits it.
accelerates. You could accelerate it, right? That would
I guess,
count.
yeah.
Yep.
True. And an object that is not moving will not move unless contacted by another object.
Right. So an object that's moving
Not
will what? Keep moving. That's what you're saying. Unless something else stops it or accelerates it, right? Right? I cannot type today. I didn't sleep as much as I thought I did. And then an object, so vice versa with an object at rest. Is that what you're saying? Okay.
Vice versa.
Yeah, there you go.
Vice versa.
An object
It's vice.
stays.
Vice.
I cannot type today. At rest. I cannot. Look at me. I threw a K in that word that doesn't it stay. An object at rest stays at rest. And it's the same thing, right? Whenever you write like ... that means the same thing. So it saves you writing. All right, let's look at this next one. This is Newton's second law. Lily, you want to put that in your own words for me?
The total force of an object equals its acceleration times its mass.
Okay. Total force. Everybody agree, or does anybody have something different to say?
I agree.
Okay. Total force of an object equals its, what'd you say? Its acceleration, right? Times its mass. There you go.
Oh, wait, there's no line.
Yeah. What? Whoa. Really? Yeah, gosh. I cannot type today. I also can't see anything I'm looking at. All right, so, and how about this very last one? Oh, lots of them. Okay, so you and your friend are walking down the sidewalk together. You alone are towing a wagon full of wood and bricks for a fort the two of you are building. You check your watch and realize that you're due to be back home in 5 minutes. The wagon's very heavy and you're pulling as hard as you can and it's slow going. You don't think you'll be able to make it home in time. You can think of 2 ways to increase your acceleration to get home while not losing anything you're hauling. So wait a minute. I'm going to have you each give me one of your choices. So let's see. Traveler, why don't you give me one of your choices? What's one of your choices? Get your lazy friend to help. I like it. Get your lazy friend to help. I cannot. I'm telling you today, it's just not a good, okay. Not wrong. I'm a bad typist anyway, but I'm like really bad today. Okay. And what's the other choice that you have, Jack?
He kind of put it vaguely. I kind of put mine in more detailed. And
Okay.
falls with the helping. Well, can I say both of them since they're both kind of...
Yeah, go ahead. Go ahead.
Can I go?
Yeah, let him finish and then you go. Go
My
ahead.
friend carries some of the load, mass. And then the other one was I continue pulling while my friend pushes, combining.
Oh, very good. Okay. So those are 2 possibles. Did anybody think of a third?
I did.
So wait a minute. Hang on a sec. Traveler, when you said get your friend to help, how were you having him help? Push or pull?
Push.
Okay. Push. And then the other option was what?
I have no pull.
Push or pull. So that's kind of 2 ways to look at helping. All right. Drew. Wait, Lily was next. Sorry. Then go ahead, Lily.
Have your friend to help that will increase the force on the wagon.
Okay. Good.
Okay.
Good. That's pushing and pulling.
I have 2 possible things.
Okay.
Either one, both of them could lift up the back of the wagon and then
Run.
kind of like carry it
And run.
Yeah, and run.
No.
Or they could just ride down the hill. Is it up or down the hill?
It doesn't
I
say.
was going to do
Okay,
hill and I was
just
going to
push it like a very, very crappy bobsled team.
Okay.
And then you just jump in.
And then jump.
Cool
How about this
And
one?
there's one more.
Okay.
You just leave the wagon behind.
That's what I was going to say. Stash the wagon or the load
Screw the
and come back. Watch your language. Come back
that word.
for it. It's not a great one. All right. So which would you pick? Who votes for stashing the wagon versus having a friend help? Trav's gonna stash the wagon. Everybody else gonna have a friend help?
Yes.
Everybody else gonna have a friend help.
Yeah.
Why? So why would you choose to stash your wagon? Because it's 5, right, dude.
How far is your
So we now know that Trav's mom is the scariest mom. Because she is. Because Trav is going to stash the wagon. Trav is not going to risk. I love it. Excellent. All right. Well, you guys did really well. Do you have anything else to add, Jack?
I'm giving that one. If it was on a hill, I would say push it back up the hill and use it like a bobsled and ride down the hill.
Yeah, there you go.
And the other one is, have you ever seen the movie Cool Runnings?
Yes.
I haven't.
The Jamaican
Watch it.
bobsled team.
Yeah.
Excellent.
Bobsled team. I'm like, Cool Runnings.
All right, so we're gonna go ahead and say that we're done for this, and we're gonna move on to our lab. So I'm gonna stop the recording, but y'all can wave goodbye because I have your camera this way. Goodbye. Okay, and we're gonna end it. Bye, guys.
Be gone.